My name's Keith Sauer. I'm an engineering manager here in Houston, and Pranay is our principal thermal architect. And he's going to talk about thermal cooling, liquid cooling in a minute, but I wanted to set him up and talk a little bit about our engineering team here in Houston that's responsible for developing our chassis that you see on all of our servers. So my team is made up of mechanical, thermal, tooling, and packaging engineers. And so the mechanical engineers design all of the injection molded plastics, the stamped sheet metal, and the die cast metal parts that make up the servers. It includes things like hard drive carriers that are toolless and allow you to swap out hard drives quickly and efficiently. Rail kits that allow you to pull the servers out of the racks so that you can service them. Cable arms that handle all of the external cables that allow you to pull the server out and without turning it off. So the mechanical engineers do all of that. The thermal engineers design the thermal solutions that include the fans, the heat sinks, and the cold loops, things that make up all of the things we have to do to cool the servers. The tooling engineers allow us to mass produce chassis all over the world in high volumes. We're building 4 servers a minute, 24 hours a day, 7 days a week. And we're assembling those in factories across the world. So the tooling engineers allow us to mass produce these parts in high volume, low tolerance conditions so that they can assemble anywhere in the world and go together without any issues. Once we build and test the servers in the factories, then we've got to get the servers to the customer. So we've got packaging engineers that design all of our boxes and cushions and crates needed to ship these servers around the world on boats and planes and trains and automobiles and get there in a way that when the customer gets them, they fire them up and they work every time. As we're designing these chassis, our biggest challenge coming up is the cooling of these boxes. And back in the good old days, about 3 years ago, thermals was an afterthought. We basically shoved as much stuff as we could in a 1U or 2U box, and then people asked us to shove more stuff in there, and we were like, no problem, we'll figure it out. We built a prototype, we would test it. Things might get a little bit warm, but we would throw an extra fan in there, maybe add a more high performance fan, get a more efficient heat sink, go from an extruded aluminum to a heat pipe to a vapor chamber. And then we would design baffles to direct the airflow where we needed to cool the server. We just figured it out, and we're no longer able to do that. And so I think that sets Pranay up to talk about our thermal challenges, and I'll turn it over to you.
Thank you, Keith. So as Keith said, my name is Pranay Mahendra. I'm a thermal engineer in the HPE Compute Group. And as Keith pointed out from a few years back, yes, everything would be designed, and all I had to say was, thank you, and just take it and do whatever with it. But that's no longer the case. So to begin with, I will jump into air cooling. Yeah, probably you may be thinking, we are here to talk liquid cooling. What are you doing? Air cooling? So, but liquid cooling, yes, that's coming up. It's inevitable. We have to go to liquid cooling eventually. But where are we today? Where are the customers? That's the thing we have been trying to study or understand from our customer base, where they are. What can air do for us? Or what can air still do for us? So for 3 generations, I would say, in a 1U form factor, we have developed heat pipe, heat sinks, and I would say extended volume or extensions that go in front of the DIMM section to capture as much heat as possible, or additional airflow, surface area, to cool as much processor power as possible. And we are kind of out of the room space, and we still cool. Air cooling is still very prominent, so we still use it. So the next question was like, what can we do next in this space? Can we take it or cool even higher wattage processor? How high can we go? So that's where we kind of came up with the concept of the closed loop liquid cooling, wherein we remove the heat sinks from the processors, install the two cold plates with pumps in there, and then we route the radiator that still sits inside the server between the hard drive backplane and the fans. So obviously the space is limited. Like, I don't get what I would like to. So to make this fit in the space, I go from what I call the dual rotor fans or the counter rotating fans, and I have to cut it down to a 28 millimeter fan so I can fit my radiator and still get, or I would say, get better cooling than my performance heatsink. So if you guys,
So these are still air cooled.
I still call this air cool.
Yeah, because it still has a fan in the chassis and everything. It's just, you're moving the heat first.
Yeah. So this is basically, and I have just kind of beaten it up left and right, and you can see. So this is what it is basically. It's just a radiator connected to the cold plates with the pumps in there, and we pump the liquid and stays within the server, and it is air cooled still because nothing is going outside the server.
Is that stuff you developed yourself, or did you use a company like a JetCool to?
So we used one of our vendors. We kind of gave them the design on what we are looking for or the dimensions and stuff we have. It said, hey, something like similar to the heatsink.
Right.
So yeah, we just asked one of our partner vendors to say, hey, this is our requirement. This is what we like to see. And this is the pump power requirements and stuff.
Okay.
I see that in the 2U where you have the extra space, you have this third tier called Max Performance.
Yes.
Is the closed loop for 1U sort of a clever way to approximate max?
Yes, you can say that's a closed loop is kind of a max cooling in a 1U space.
Well, but does the closed loop ever reach a boiling point that it needs to be refreshed? Is there a half-life for the coolant?
So typically, say, what we use in there is still PG25, like what we use in DLC. And we do have some extra reservoirs. We have extra coolant in there so we can keep it running. And typically the life cycle is, or lifespan of it is close to 6 years kind of thing. But there have been, and that's being conservative, just so that, hey, we don't want anyone to run into kind of heat issues and stuff, but that can be extended, or it has more.
Because over time you start to diminish the quality of the heat transfer, right?
Yes. So 6 years, we should be able to get that. And then after that, we may start seeing some impact. But yes, it's 5 years for sure. So depending on the life cycle of the product or what we are doing, we do have runway for the 6 year. From a recommendation perspective, we say, hey, just swap it out at that point.
And once again, that's at the back plane, the closed loop. That's where the radiator is.
So radiator, radiator basically sits behind the backplane. I would say it's in the space behind the backplane where the fans go.
Yeah.
So the fan is right there. So we just removed or reduced the depth of the fan and we dropped the radiator.
Do you reference any or recommend any like data center airflow adjustments or anything like that?
No, for this, no.
Yeah.
No, this is just from a pure server perspective. What can you do? Hey, if your performance heatsink, for example, I'll just pull numbers. Say you can do 270 watts or 300 watts. Now, if you use this because of the additional surface area and more air capture, you can cool 400 watts, 450 watts also on the processor.
This is a neat kind of air cooling that uses liquid.
Yeah, and then in a 2U space, because I'll kind of stick with 1U and 2U discussion. So as you see, we have brought it up, it's a max cool, max performance heatsink. And obviously this was the other thing we kind of pushed on, like, hey, what can we do in 2U space? How much can we push? And when we brought this design up for the first time, the obvious question was, what are you doing? Nobody can service the memory. And that's not acceptable. So like then we optimize the height of the fins on the top such that we can service the DIMMs, not very easily the way you would without having these fins in there, but still without having to remove the heatsink, you can still get your fingers easily, get to the memory slots and remove the DIMM. It's not as easy as not having these things, but if we need better cooling for a higher wattage processor, or you need to lower your fan power consumption, you have an option to use. All right, with that said, obviously the fans, I just kind of listed there. There's nothing new. It's just whatever has been done traditionally from the fan perspective. You define it based on the impedance system and the components that we are going to cool. Getting into the direct liquid cooling, or the DLC as we know. So I have a cold plate module of where we are today, or how we install it. Basically, again, we remove our heat sinks, we have our cold plates, and then this is one of the way we route it out of the system. So this bracket can go into the PCI slot so that it keeps it sturdy. And well, you look at it and say, hey, these tubes are just too short. You just can't get to your manifold, which eventually, or the cold plates need to be connected to the manifold. So what we did here is we designed this common module so it can be used on any of our chassis, because we have different depth chassis from small to medium to large. So based on that, if we just get this out of the system, and then we have an extension tube that runs from here to the manifold in the system. And then the manifold connects to the CDU, or the cooling distribution unit, that sits on the bottom of the rack, and that in turn is connected to the facilities water.
Are those quick disconnects, self-sealing quick disconnects? Or,
Yeah, these are the quick disconnects.
and they're self-sealing?
And does the loop run, are they serial or parallel? So
this is in series. This is not parallel.
So one CPU is going to run cooler than the other one.
Yes, and typically it has been in the 5 to 7 degree difference range. Yes, you can do parallel to kind of to balance the temperatures, but even after that, like, we still run it overcooled. The processor temperatures are really cool compared to what you can get on the air cool.
Okay.
And so the liquid coming in has to be what temperature?
So it can be up to 40 degrees. So depending on the data center,
Celsius.
40 degrees Celsius.
What kind of deltas are we getting from the effectiveness of the cooling liquid versus air?
What levels of delta, meaning the table drop? So so typically the air cooling will keep the processors at the defined temperature, or the target temperature as defined by the vendors, like be it Intel, AMD, or NVIDIA. So it keeps it right there. But what liquid does is, if depending on, you can just set the LPM depending on the vendors. You can have a delta P operating pressure across the CDU, or you can define your liquid through there, and you can easily keep it 10 degrees below the operating point. So you're overcooling it to get into, say, the turbo mode, or you have your turbo frequencies. You have a base frequency for the processor, and then turbo above that is opportunistic. You can get in there because you're keeping it more than 10 degrees cooler than where it is supposed to run. So obviously, as I mentioned, liquid DLC requires the liquid in the data center, your cold plate modules, rack manifold, and the cooling distribution unit. So yes, there is some CapEx involved early on, and the data centers are moving towards it, but it's a slow, gradual adoption. And when we talk about liquid cooling, one of the biggest questions that come up is leakage, because leakage just freaks everyone out. So as a first step, what we have done is we have implemented leakage detection inside the server, where we have the leak detection band, or the mesh, around both closed loop and the DLC. And these loops are connected to the system board with a power connector. And it's the same power connector that provides power to the pumps on the closed loop. And it also can, if it senses leakage, it sends a signal to the system and the ILO, and the system is immediately shut down to prevent it from burning up or whatever catastrophic failure may happen. And obviously, the system will not be able to reboot, or it will prevent system boot until the bit is cleared. and all these actions are logged down in our ILO and all places. Now, we have talked about liquid cooling being really expensive from a CapEx perspective, and there are concerns of leakage, which we have to address. So why liquid cooling? If I have to kind of define it in a very simplest of terms, I would kind of place it like this, where number one, power and performance. So as we know, the power of the GPUs or CPUs, everything is just going up. And not just that, sometimes with the increase in power, to maintain a certain frequency, the case temperature as defined when the vendor goes down. So it's a double whammy at that point for us. So for that, for a reliable operation of that component, we need liquid cooling. So that's the need of the hour at that point. And then the other thing, as I just mentioned, turbo. So say if you have a processor that has a base frequency of 2.8 gigahertz, but a turbo frequency, a boost frequency of 4.2 gigahertz, with air, that turbo is opportunistic. So yes, can I get the turbo frequency? Up to a certain point with air, but I am going to consume a lot of fan power, or I have to spin the fans almost at 100% to get to that point. But with liquid, we save the power. We can be in turbo mode for a sustained period of time.
What does your PUE look like when you're doing that?
So that's a tricky one because from a data center perspective, right? So we are kind of doing this from a server perspective, and we are trying to piece that. I'm trying to deflect this just for the reason I don't want to make
It sounds like it gets better when you're going into this mode because you're driving the fans down, right?
Yes, definitely. It gets better. And I can show you, I have a couple of slides where I show what gets better or how we estimated certain things. And I have a couple of slides that I can show you how. And I've kind of kept it from a power consumption perspective or what we save from power.
I'm just looking relative.
Yeah.
You're talking one server liquid cooled. I'm assuming that if you have a rack full of servers, you don't have a hybrid. You don't have some that are air cooled, some that are liquid cooled. And if you do, would the air cooled be on the bottom and liquid cooled be on top? And how many, well, last question being, how many liquid cooled servers can run in this environment?
So typically, we do not ship anything that's a mix, but the customer can do it. So at that, so what Scott said is there are switches in the rack. Those are air cooled.
Top
Top of the rack switches. So to answer your question, today as it stands, everything air cooled goes in the top of the rack and servers are at the bottom. And it's kind of easier also because you have your CDU at the bottom. And so you just connect it, but you have the capability to connect it from wherever.
I mean, I'm sure actually you could put a mid-rack
Yes.
in there.
Yeah, you can.
Yeah.
So it doesn't matter. Because the manifold is designed such that you have so many QDs, quick disconnects. So it doesn't matter where you install your server, you can connect it.
Well, I mean, the liquid cooling only covers the CPUs, doesn't cover the rest of the system. It's generating heat as well, right? So
Yes.
that's got to be taken care of. And there's a ratio that's discussed a lot. Sometimes it's 70-30, sometimes 80-20.
So typically, yes, the 70-30 is on the higher end, but it can be 60-40 also depending on what kind of processors you use. And if say, for example, your total server power consumption is 1 kilowatt, but your processors are only 300 watt processors, or if you are dumping only 600 watts to the processors, to the liquid, then you're 60-40 split.
Now, and this line that you're talking about, we're not going to discuss the NVL72 kind of stuff, right? That's a completely different line of servers from HPE. So we're not talking about the big NVIDIA boxes. We're talking about the H100, H200.
Here, what I'm talking is primarily the mainstream or enterprise level servers, which are processors are the key, and not even everything else is air cooled. Even the PCI cards or PCI version of GPUs are air cooled. Right. Yes, once you go to your NVL4, NVL2s or anything on a board kind of a MGX, then that's a liquid. But what I am talking here is primarily from a ProLiant mainstream enterprise customer.
Thanks.
Can you talk about the efficiency side of it?
I will show you something.
Great. Now I've done the perfect way, everybody.
And to answer your last question, yes, if you have a 42U rack, you can easily fill in 40, 42U, 1U server, 42 1U servers in there without any.
How many servers does that cooling box handle?
So that typically it depends. There are different capacities for the cooling distribution units. They can go from 80 kilowatts to 150 kilowatts. And if you are only dumping 1 kilowatt per server, say if you have 500 watt processors, so you can just put in, you can connect 100 servers also if you are capable of doing it. Typically, then you'll have to kind of do all kinds of tubing to the next rack and stuff. So it just gets complicated, but you can do it.
And
So
how do they lock together from the unit? I saw the ends on that. Is it like a snap lock? Is it a twist lock? How's it work?
You just press it in, and it's a quick disconnect. It just locks in place.
Okay.
It's just
When it gets disconnected, let's say you're taking down a server, it gets disconnected.
so you just have to kind of
Have
pull.
like a cup underneath or something like that?
No, typically you. Oh, I don't have the females. Yeah, they are dry disconnects basically.
Okay.
So you just pull and just comes out. It just dry. Nothing drips from there. Dripless also you can call it.
Okay.
Okay. So again, so power performance is one piece of the thing. And again, what we talked about, hey, if you have a 42U rack and I want to fill it up because space is premium for me, I need to use up the density I have. I can't go to a 2U server or anything. Yes, that's where liquid cooling helps. And then finally, efficiency, or you can even think about from a sustainability perspective that, hey, how can I help from a sustainability perspective from a cooling side? Oh, I need to lower my fan power consumption. That's the key. And how can I do that? If I use liquid, it will be I will be able to lower the fan power, because the processors are typically are driving the fans, and when we go there, the fan power drops, or the speed drops and the fan power drops.
Is this also being designed for the GPUs as well as the CPUs?
So yes, in the mainstream, we are doing on CPUs, but we do have other servers where if you have your GPU on the system board like NVL72 or NVL4, or we have seen earlier the DL384 kind of system, we can have.
Yeah, because you have two factors: your thermal footprint as well as the power footprint. You're trying to decrease both those curves, right?
Yeah. So because the power is going up, now we have to cool it regardless based on that. And so that said, one other thing I wanted to kind of touch base on, or would be key in the considerations, is the data center rack power. So I just kind of took a screen capture from the Uptime Institute survey that they did in 2023 and 2024, and they compared it. Obviously, as we can see here, the rack densities for the lower kilowatt racks, like less than 10 kilowatt, is going down. It went from 41% to 34%. Similarly, the 10 to 14 has gone down, and then we are getting an increase in power. The new data centers that are being designed, the power is being upped on the per rack basis. But if you look at it, even between 2023 and 2024, the racks that were surveyed and are below the 29 kilowatt number are 86% in 2023. It only went down by 3%. So 83% of the racks are below 29 kilowatt. So obviously it's an easy answer. If you have liquid in your data center, if your rack density is very critical to you, if you need to fully populate the rack with servers, and if your rack power is greater than 29 kilowatt, yes, you can do liquid cooling. But what if my customer has a rack that is less than or equal to 19 kilowatts, and they're only populating 20 servers or less than 20 servers because of the power capping at this instance? Yes, in the future, things will change. But if they're only able to support only less than 20 servers in the rack, and if they have no liquid in the data center, what can we do? And that's the other aspect of things we are looking at also from air cooling, or that's why we are still focused on air cooling as well. How do we balance this out until customers get to the liquid cooling side of things? And if you look at it, less than 19 kilowatts, you're still 76%. It's a huge number still in that range for the power. Okay. So that said, with air cooling, liquid cooling, and the data center power, so one attempt we have done is to show how, or at least show a trend on how things or the power will drop. So what I would say here is, what I did is I considered a 1 kilowatt as a reference, just because this can change with depending on the processors used or the configuration we have for the server. So when we have, say, a 1 kilowatt rack and also 1 kilowatt server, and we have a 15 kilowatt availability for a rack, so you can only install maybe 12, 13 servers in that rack. So if I have a 1U server with my performance heatsink installed, I will kind of use a huge, very high power number of power wattage. And if I use a closed loop, you can see it drops. And further, as we go to the 2U and DLC, we have a trend that shows, hey, you guessed, you have reduced your power significantly going from 1U to 2U and even DLC. And obviously, you can see in this scenario, because it's only a 270 watt processor, my 2U heatsink can do almost similar to what DLC can do, but the DLC isn't still in 1U space. So you can have 40, 42 servers in the rack, and my 2U, you only get 20 servers in the rack at that point.
So going from the performance heatsink to the direct liquid cooling, this is a 1200 watt?
Something like that on the, yeah.
Rack.
Yeah, and yes, I have that number there, but it's kind of a reference, so it won't be exactly the same. It will depend based on the mileage, or you can call it, or what processor you have, what configuration you have in the system. Things can change, but that will go down drastically.
All these are compliant with OCP, right?
Sorry?
All these are compliant with OCP?
Compliant, what do you mean?
They're using reference specs. They can, like, if you have an OCP environment and you decide you're going to go multi-vendor, say.
Yes, we are getting there. Today, how we ship our the DLC is we have a complete rack configured in our factory and send ship it to the customer. But yes, we are moving towards, yes, we are open to that OCP kind of thing where you can start mix and match. And Mr. Schaefer is very high on that also.
So wait, so I know we're talking about liquid cooling, but I can't help it, right? He's gonna like, so these are the two bars you should look at. Please ignore liquid cooling for a minute, right? You saw in the previous chart that most customers can't deploy more than 29 kilowatts in a rack, right?
If that.
So if they can't do that, why are they buying 1U servers? Because 1U servers cost them a lot more power than a 2U server in power to cool them, not in power to operate them. In fact, his design, which I love this, the server's a kilowatt regardless. That's a baseline, right? So you have the same CPU, the same memory, the same SSDs in both servers. 1U, 2U. You pay an extra 100 watts a server, 1,000 watts total in this setup that he built with 10. 1,000 watts just for the fans. Why are you doing that? Is my question. Only use 1U when you need it. When you know you absolutely have to have it, when you're willing to pay that extra cost for the fan power, go for it. Right? When it's needed, absolutely. But if it's not needed, go here. Go down to the 2U. Trade off density. My message, and I don't know if it's Pranay's message, my message is we have chased density for too long, and it's just caught up to us where we can't efficiently power it anyway. Right? We can't, our racks can't handle it.
Well, data centers space is sold by the kilowatt, not by the square foot.
Yeah.
So you're right. I mean, what you're saying is spot on. I mean, it makes no sense. You're buying the power. You're not buying the physical space, right? So.
Right.
And if you have liquid cooled DLC, yeah, sure. Then go for your 1Us, and if your density is very critical, you have 30, 40 kilowatt racks, yeah, populate them.
It's just there are certain scenarios where density is really important. I'm thinking like financials in Manhattan, you know.
Or HPC class workloads, right? They're big Monte Carlo.
I deliberately picked.
Actually, I'm going to disagree with you because So the power in, let's say, the New York Metro, and I speak from experience on this one, the financials they pay exorbitant amount of kVA. The constraint is power, not space. I got space. It's the power that's the constraint. So designing for power, you can go the extra racks and go with it's not about, it's about that amount. I mean, you're paying hundreds of dollars more per kVA than you might in, say, I don't know, pick a Utah or something, right?
Texas, turns out.
Texas,
pretty low cost of power. But look, I'm not against 1U. I'm not against it. I'm saying use it when you need to. Think of it, we should think of 1Us as more specialized than we used to. We used to think of them as the general purpose pizza box server, right? That's what, I grew up on, right? But now I'm saying, they ought to be able to think of them as a little more specialized. Or when I really need that density play, they're the great solution for it. But when I don't, I should be using 2U.
So from there, try to make another attempt on this slide where the previous slide showed the total rack power or the cooling power in the rack for 12 servers. What I'm showing here is still the same 5 scenarios, performance heatsink to DLC. On the bottom here is the purple and the yellow together are the cooling power per server. And the reason the DLC has 2 different colors here is one for the fans that are in the system, and then per server basis, how much power are you consuming from the CDU perspective or the cooling distribution unit. And especially now, given you only have, say, 12 servers in the rack, whatever the CDU is operating at, if you have 40 and you're operating at the same power, you are consuming really low from a CDU perspective. But if you only have 12 servers, you're at least consuming a certain amount on a CDU pump also. So per server basis, you can see the trend still what we saw previously with the 2U max performance heatsink and the 1U DLC at similar level. This is still lower, but a similar level, but this is only for this scenario. If the power of the processor goes up, this kind of stays almost similar. This starts going up. So you get bigger impact or you see more improvement.
Yeah, the closed loop, right? There's not additional impact for the cost of capital equipment and bringing liquid to a cage. The extra, that tiny little bit of additional power savings you're getting from the 2U air cooling going to the DLC in that scenario, the amount of money it will cost you to get the water in an existing data center to that rack makes it a ridiculous choice, honestly.
Right.
There's no choice.
No, but it depends on what you want. If you're looking at a, say, 500 watt processor, 2 of those in there to cool it, then, yes, it's dependent on the requirement, as Scott was, if it's needed, if you know you can use it, or just compare and see how and when it makes sense.
Yeah. But the economics of it.
Yeah, exactly.
Like even at GTC, Jensen was talking about that you're going to spend just as much on liquid cooling infrastructure as you will on that superpod, right? In many cases. So same thing as the liquid cooling. It shouldn't be underestimated what it costs to get water to a cage. It's not fun.
So CapEx versus your OpEx, how much are you going to really save eventually? That's the math that needs to be done.
Is there a difference between the regular powered or the high power systems now? Because pretty much everything is like switching over to high power, high voltage, talking about like CPU, storage. So is this even considering regular low?
So we still have a lot of customers who are in a 205 watt processor range.
Yeah.
They have not even kind of gone to a 500 because what they need from a course perspective, your frequency perspective, they are still right there. So air cool, and if they don't have enough power in the rack, air cool is their best friend still.
Still a good sweet spot. Okay.
So those are the things that need to be evaluated. So this is just an attempt to show, hey, just a reference. Think about these things also. It's not just like black and white that, hey, air, I'm jumping to liquid. Like, no, just evaluate where we are, what we are trying to achieve, and how we are planning to go there.
Yeah. The only piece of advice I'd say for you guys as you're going to market with the right most with the DLC is just make sure your sellers are talking to the customers, data center providers and facilities people early in that conversation, because you don't want that left to the end. I mean, it's not that it can't be done, and not that there's not use cases for it, and that some folks are going to be great at it. It's just that is something that must be discussed early on. That's kind of what we've learned over time.
Yeah, agree. So one thing I've kind of attempted to do here or kind of shown is that this top light blue section also. And the reason, and this is an estimation and an estimation only, because the data centers are different, they are designed the way they are. I just wanted to show if there is a typical data center, obviously, which kind of uses your cooling towers, your chillers, your air handling units, and if you have a lot of air handling needed and stuff, what would be the data center power per server is what I'm showing here. And if you look at the air cooling, yes, you're saving server or data center power per server, even going from a 1U to a 2U max performance. There's a little server saving, but if you go to DLC, you can tweak your settings. You can change things in there that can help save more power. It's not just at a server level, but if you get into DLC, things that need to be considered is what is your data center efficiency or how you're operating it, or as was mentioned earlier, what is the PUE and where you're operating that.